My name is Acep from Engineering Department of PJB Indonesia. Today I'm going to present failure analysis and lasting wear of last take low pressure steam turbine blade. To save on manufacturing costs, technology for the last take low pressure steam turbine blade tend to use an integral surf blade or ISB with a lasting wear on the center so that the blade can be maintained but stability due to vibration and deformation can still be achieved. The materials commonly used for lasting wear is PH174, which is steel with a martensitic precipitation and hardening. This material has good mechanical properties, good corrosion resistance, and good wear resistance. But a number of vulnerable failures occur at the last stage low pressure turbine blade. In example, fracture on lasting wear, fretting on throat, and crack on roots. According to Li Xiao et al. 2019, the break of lasting wire was driven by continued impact of the tack, weld, lasting wire, and stub. While the type of lasting wire that is welded directly to the blade, high stress concentration occurred at that point, which also triggers crack initiation. This is mentioned by Posey et al. In 2010. Both sources of failure reference conclude that the failure mechanism is from the mechanism of fatigue. In the present work, a root cause failure analysis study was performed on lasting wire of low pressure turbine blade. The aim was to get understanding on failure mechanism and to prevent future events to occur. This is object of study, low pressure steam turbine with a speed 3000 rpm, length of last take blade is 900 mm. Working condition inlet and outlet pressure is 1.06 and 0.0063 MPa. Inlet temperature is 358 Celsius. This is methodology. We are using maintenance history and visual inspection to get the maintenance data, OAS to get a chemical composition, microstructure image, microstructure topography, and chemical element of steel and deposit are analyzed. And we check hardness and distribution. And the cyclic stress evaluate using harmonic analysis simulation using Ansys 2019 R2. This is the history of failure. On 30 November 2018 found an increase in conductivity from the online analysis measurement in the condenser that very quickly. The unit was decided to be shut down and found that the condenser pipe was leaked due to being hit by the impact of broken lasting wire from low pressure steam turbine blade. Further investigation on turbine side found that the lasting wire stub at the blade was broke. There are two installation types of lasting wire on the blade. The first is with the tack weld that functions as a stopper between the lasting wire and stub, and the second is by welding directly into the blade. So this is how we do maintenance. Maintenance was carried out in the manner of perform foot weld to replacing the tack weld at the end of the lasting wire. The welding method is using filler ER410 without preheat and post-wet treatment. In December 2019, during inspection period, found foot weld on the lasting wire have broken, especially in the heat affected zone. You can see here. Lasting wire and stub that are not welded, both tack weld and foot weld do not fail and never fail. From the maintenance history, it can be said that the material has a fracture in the area around heat affected zone, both that occur in tack weld and foot weld, indicating that possibility that the welding process triggered failure. So we take a 3 sample labeled as A, B, and C. This is the result of visual inspection. Typical fatigue fault where the beachmark pattern is clearly visible, initiating crack starting from area near the heat affected zone, then very wide crack growth, and a final fracture. The three steps of failure indicates that the lasting wire has broken due to fatigue. The final fracture area is quite small, about 10% of total area, which indicates that the stress is quite small compared to the material strength of steel. This is the result chemical composition. The chemical composition of the sample we can see here are within the range of standard chemical composition of GB and ISDM or other standard. You can see chromium 17.04. Under the check using ACM and EDS, it appears that this sample has a composition close to the composition of OES results. This is another result of ACM. We can see visible crack initiation, beachmark pattern. Another type of fatigue failure, we can see transgranular fracture here in the base metal. So this is another microstructure image. We can see ferrite martensitic in the base metal and martensitic in the weld metal. Microstructure shape of the lasting wire base metal around heat affected zone is smoother, or there is change in the shape of granules. This indicates that the lasting wire material around heat affected zone area is softer. We can check by hardness test. So this is hardness test. We take 5 points with direction in X and Y. Average hardness of the sample is almost the same, about 300 figure, which fall within standard material range according ASTM standard. The lowest hardness is found in that area around the weld metal. This shows that the lasting wire material on the fracture surface has decreased in hardness due to welding, and this shows that after post-welding there is no post-weld heat treatment. You can see here in Y at the 5. The hardness of the material or the fracture become more soft and cracked. So for stress evaluation, we are using fluid volume mesh all-stick CFD model of low pressure steam turbine blade using 5-blade system to reduce resource on the Ansys analysis. A counter pressure result last stick blade from CFD molded we got, and imported pressure for harmonic analysis. So this is how we do validation model for CFD with a spirit calculation of turbine power from actual operating data and the CFD model. So we got difference of 4.1%. So stress evaluation plotted using frequency 50 operation frequency, natural frequency, first natural frequency and second natural frequency. The intersection between the excitation frequency length and the vibration mode curve occur at the ratio of 3 times and 5 times. So the result of the higher stress amplitude position are close to the actual lasting wire failure position, where actual failure is 35 mm from the edge and stress concentration is 24.66 mm from the edge. So we can conclude fractography and macro observation so that the lasting wire is broken by the mechanism of fatigue failure, where the failure begins with the initiation of crack in the area around the weld. Clearly visible beachmark pattern in the crack propagation area. The percentage of the area of final fracture show that the dynamic stress quite small compared to the strength of material. Improper maintenance procedure especially welding further trigger an initial crack, then the initial crack get concentrate cyclic load causing laser wire broken. Recommendation: due to the nature of crack propagation in the laser wire, which most of time occurs in the embedded crack inside the heat affected zone, it is highly recommended not to carry out any procedure that can initiate crack in the laser wire. Because if there is crack initiation in the laser wire, it is almost certain that the laser wire will fail without having time to inspect the crack. Inspect the presence of crack initiation by the appropriate method on the result of welding on the laser wire. To avoid cold crack, it is necessary to do preheat and post-weld treatment according AWS standard. Thank you.